All right, this is section 1 for chapter 6. So we are getting into covalent compounds. Chapter 5 was all about naming and understanding ionic compounds, and now we're going to talk about covalent. So covalent compounds in itself, they're not complicated, but adding that to what we already know with ionic compounds, it does tend to get confusing, but we're going to go through it. So this is just a review about ionic compounds. So I'm going to pause this in just a few seconds, and it's going to prompt you to answer these 3 questions. All right, covalent compounds or covalent bonds. This is when electrons are shared. They're not being pulled when they are in ionic compounds. So when we were talking about ionic compounds, remember like NaCl, table salt. The Na, or the sodium, had a positive charge, it had a +1. The chlorine, or the Cl, had a -1 charge, and the chlorine pulled the electron from the sodium, and that's what gave the sodium the positive charge. In covalent bonds, there are no charges because nothing's being pulled or given up or taken away. They're being shared. These are friendlier bonds. So when these bonds form, energy is released, and that's with kind of anything that happens ever. Energy is released when something happens. Most atoms on their own are not stable, so when they form that bond, they're more stable when they are in that bond. However, when the energy is released, the atoms are doing that to become more stable and reach a lower energy. So bond length, we talked about a little bit when we talked about periodic trends. That was the ionic radii or bond radii. So it's just the average between the 2 nuclei of 2 bonded atoms. So these are hydrogens, and the bond length is 17 pm, which is picometers. So if you remember conversions, pico was very, 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 very small. And these atoms they don't stick together and just stay together. They kind of vibrate like a spring. So if you imagine having a spring between your thumb and your index finger, and you squeeze the spring back and forth, that's kind of how the atoms are. So the energy that's required to break that spring or that vibration in between there, that would be the bond energy. So the amount of energy that it would take to break a bond. Electronegativity is something we are very familiar with already. We talked about it with periodic trends on the periodic table in chapter 4. It's also something that we talked about when we were doing orbital diagrams. So electronegativity is when it's the ability for an atom to draw in electrons. And if you remember that trend, atoms that are farther to the right on the periodic table, they have a higher electronegativity. Their ability to pull in electrons is higher. And that's because those atoms want to gain electrons. So they have a high electronegativity because they want to pull in electrons. Atoms towards the left side of the periodic table, the metals, they have a lower electronegativity. It's not 0, it's just lower, because they do not want to pull in electrons. They are trying to give them up. And that's why they have positive charges for the elements that are on the left side of the periodic table. So the Pauli exclusion principle, if you remember when we were doing orbital diagrams and we had to make sure every energy level was full before we went to add 2 electrons to each little energy level. This is the same. This is Linnaeus Pauling. He developed the same thing. So the electronegativity scale, and I attached it on the next slide, and it's also in your the second slide of your weekly calendars, is the electronegativity scale. So we're not just talking about trends anymore. We're actually giving values for the electronegativity. So they are all assigned relative to fluorine. And if you look at this electronegativity chart, all of the noble gases on the right-hand side, that group 18, they don't have any values. I'm not talking about the ones that are at the bottom down here. These elements don't exist for a long time on their own. So we don't know what their electronegativity is because they are, once they're, I don't want to say manufactured, formed, they only last for, they could last for less than a second. So anyways, the noble gases on the right-hand side, they don't have an electronegativity because they're stable. They aren't pulling in electrons at all. They have that full shell or full outer ring of valence electrons. So they don't need to pull in electrons or have an ability to pull in electrons because they're stable already. All right, so here's the difference when we're talking about electronegativity with the different kinds of bonds. So we talked about ionic bonds already. There are two kinds of covalent bonds. We have nonpolar and then polar. So in a nonpolar covalent bond, it's two atoms that have a very low electronegativity difference. And when I say electronegativity difference, let's just say we had a hydrogen-hydrogen bond. So that value for hydrogen was 2.20. And I'm going to show you this in a minute. And it's also what we're going to do together on the worksheet, minus 2.20. So their electronegativity is different, or difference is 0. This bond right here, this hydrogen-hydrogen bond, and you'll learn how to make these little diagrams right here. The electrons are being shared equally between these two bonds, or between this one bond and these two atoms. There's no pull in either direction. However, in a polar covalent bond, so this kind of subtraction thing right here, except the difference is 0.31 and 1.7. So I had to pause this video for just a second. The unequal sharing. So in a polar covalent bond, when that electronegativity difference is 0.31 or between 0.31 and 1.7, the electrons are being shared, but one is slightly more electronegative, and it's not pulling necessarily, but the electrons are going towards that more electronegative atom just slightly more. So let me show you on the next slide. So in a nonpolar covalent, so electrons are being shared equally. This is a perfect bond. The electrons are being shared perfectly in between here. In an uneven electron distribution, again, they're not separated by, one took electrons and one gave them up. The electrons are being pulled slightly more towards this more electronegative atom over here, towards the right. And they're being pulled away from this less electronegative atom right here, which makes this slightly more positive because those negative electrons are not near it as much. And in an ionic bond, they're given up completely and taken away completely. So these are technically the more weaker bonds. They're not completely weak, but these, as you go left to right, the more electronegative difference, the stronger the bond is, or the more polar, you could say. So in polar covalent bonds, when the electrons are not evenly distributed, or they aren't evenly shared, we give these partial positive and partial negative charges. So if we had, let's just say, an atom over here, not to get too technical, in an atom over here, and this one had an electronegativity of 4, and this one had an electronegativity of 1. They're still sharing these electrons between them. It's just that they're being pulled slightly more this way. And since those electrons are negative, this would get the partial negative charge, and this would get the partial positive charge. And this is only in polar covalent bonds. It's not in nonpolar covalent bonds because those electrons are being shared equally. And it's not in ionic bonds because they are completely pulling electrons or completely giving up their electrons. Whereas the electrons are still being shared for the polar covalent molecules. They're just being pulled very slightly, and that's why we say partial positive or partial negative. And if you go on to other science classes, this symbol up here is the partial charge. It is the lowercase delta. So if you remember, delta was the triangle, and we use it for like delta T, like change in temperature, just so you are aware of what that is. All right, so we have 3 separate kinds of bonds. So we have covalent bonds, we have ionic bonds, and then there's metallic bonds. We don't get into metallic bonds too much, but it is important that you know what it is. So covalent, that's when the electrons are shared. Ionic is, okay, so what? Covalent is 2 nonmetals. So everything to the right of the metalloids on the periodic table. And the electrons are being shared completely. Ionic compounds is between one metal and one nonmetal, so something from the left side of the periodic table and something from the right side of the periodic table. Those are very strong bonds. And then metallic bonds are formed between 2 metals, so 2 things from the left side of the periodic table. And often it's the same thing. So it might be like gold and gold, or magnesium and magnesium. Usually it's the same element. Sometimes it's not, though, but we don't get too much into those. So that is 6.1.